Hi, my name is Sujatha Ramakrishnan and I'm a PhD student at Ayuka. First of all, I'd like to thank the organizers for giving me this unique opportunity to present my talk as well as attend the conference in this online format. Here, I will talk about how the information in the cosmic web can be used to increase the dynamic range or the reach of a mock catalog. This work is based on a paper which is available in archive, and it has been done in collaboration with Asim Paranjpe and Ravi Sheth. Here is an outline of the talk. First, we will talk about why we need large volume mock catalogs, and then we will talk specifically about a commonly used aid for making mocks, that is the n-body simulation technique. And then we will discuss some of the limitations of the n-body simulations and how the cosmic web can be used to mitigate the limitations. Then we will move on to the method which we use to make our mock catalogs, which relies on an idea of conditioning on the local cosmic web environment. Then we will move on to a brief description of the algorithm, and then in order to test the algorithm, we will compare a regular simulation with the mocks created with our algorithm. Finally, I will summarize. The next generation of sky surveys which are planned for the coming decade cover vast area in the sky and also are very deep. Here are two examples of such vast expansive surveys. The Euclid survey covers about 1/3 of the sky, and the Vera Rubin Observatory covers almost half of the sky. Since they will cover unprecedented amounts of volume, they require large volume mock catalogs to support them. Mocks will help to compare and connect these observations with theory, and they also aim to provide better error estimates in, for example, a cosmological parameter estimation. Mock catalogs rely on numerical n-body techniques to solve dynamic equation, although there are other fast and approximate techniques also available in the literature. A little bit more about n-body simulation. The universe at very early times is mostly homogeneous and isotropic, with small fluctuations, and a linearized system of differential equations are enough to accurately describe the gravitational collapse. But as the fluctuations grow and the system becomes more non-linear, the analytical approximations are no longer valid, and we need to increasingly rely on numerical techniques to solve systems equations, especially for recent times or redshift close to zero. One of the limitations of creating simulations, especially the large volume ones, is the problem of resolution. The n-body technique solves gravitational dynamics between system of n number of particles. The computational complexity in running such simulations sets limit on the number of particles we can use to run the simulation. Typically, each of these particles have a mass of billions of solar masses, and the cosmological boxes are of the size that ranges from tens of megaparsecs to hundreds of megaparsecs. These current volumes of simulation are already pushing the traditional computers to the edge of what they're capable of. So simulating larger volumes with same limit on the total number of particles means that each particle will have a larger mass, and thus each gravitating object will be made of small number of particles. Here, for example, we take a look at inside a large volume simulation where a dark matter halo in which galaxies reside is resolved with very few number of particles. Here, for example, we have a comparison with another halo from an actual simulation which is comprised of 100,000 particles and has been well resolved. poorly resolved halos makes it difficult to decipher properties of the individual halos. For example, the shape of a halo, its angular momentum, or the density profile of the halo, or its dynamic structure. These properties are typically estimated from the information which these particles provide. In this talk, we will look at 5 such properties, each of which are condensed into scalar dimensional quantities for convenience. These are the halo shape, the halo spin, which is a measure of angular momentum, the halo concentration, the velocity anisotropy, and velocity asphericity. Even though these are small scale properties, they can create uncertainties in the measurement of large scale quantities. Let me explain this in the next slide. For example, the 2-point correlation function of dark matter halos of identical mass but different shapes will result in different clustering strengths. This is exactly what is shown in this first plot, where the 2-point correlation function has been plotted as a function of the separation, and we can see that for spherical halos given by blue, the clustering strength is higher than elongated halos, which is given by the red curve. A similar split in clustering strengths can be seen for the higher and lower quartile values of other properties, as shown in the other plots. And such a split is called the halo assembly bias or secondary bias. The term halo bias refers to the large scale clustering and is defined as the limiting ratio of the halo matter power spectrum to the matter power spectrum at large separation scales. It has a monotonically increasing dependence on mass, as shown in this bias versus mass plot, and this trend is analytically well understood in the theory of peak background split. The secondary dependence on beyond mass halo properties is termed as assembly bias because it is often thought to be a result of the assembly history of the halo. In simulations with unresolved halo properties, this halo assembly bias signal would be absent or not well defined. These uncertainties will creep into analysis that rely on summary statistics. For example, a cosmological parameter estimation done with the 2-point correlation function of galaxy clusters. But there is information in the cosmic web environment that can be used to mitigate some of these problems. This is the key idea of the talk. So what do we mean by cosmic web environment? For which let's take a look at the schematic representation of the large volume simulation again and zoom in not all the way down to a halo but down to its environment. What we see is a web-like structure of dark matter, which is often called the cosmic web. The dark matter halos are found embedded in this structure. They may be situated in a region where they experience uneven tidal forces. For example, in the middle of a filament, or they may be under the influence of a large massive halo, or they may experience tidal forces, equal tidal forces in all directions, as would be in the case of a dark matter halo somewhere in the middle of a void or at the center of a node. In order to quantify the cosmic web environment, or rather the anisotropy of the cosmic web environment, we use the tidal anisotropy alpha, which is computed using the eigenvalues of the tidal tensor. It is basically quantified by the sum of squares of the differences of the eigenvalues of the tidal tensor. This quantity is measured over a scale of 4 times the radius of a halo, which means that the large volume simulation with poor resolution, the tidal anisotropy around a halo would still be sufficiently resolved even though the properties themselves are not. This is shown in this plot where the mean value of different halo properties is plotted as a function of mass for two resolutions. A higher resolution simulation shown by empty markers and low resolution simulation shown by solid markers, and we see that below a certain mass the low resolution simulation is no longer able to accurately compute the halo properties. For all these halo properties, this mass cut, or in terms of numbers, this number cut would correspond to a halo which has less than 500 to 1000 particles. However, in this region, if we look at the final subplot which shows the average value of the tidal anisotropy as a function of mass, we see that there is convergence between the high resolution and the low resolution simulation, even down to 30 particle mass cut. We will see how we can make use of the values of these resolved tidal anisotropy to recover the unresolved halo properties. A number of studies find that tidal anisotropy has an important role to play in the assembly bias signal. In previous work, we have shown that the assembly bias signal vanishes for halos in a fixed tidal environment. If we denote the internal property by C, the mass by M, and halo bias by B1, then the probability distribution of C and B1 shows conditional independence between the halo bias and halo property. That is, the joint probability distribution can be written as the product of their individual probability distributions when conditioned on mass and tidal anisotropy. A likely explanation for this structure is that even though we talk about the dependence of halo bias on halo properties, there is no physical connection between the two. The apparent correlation which exists between halo property and halo bias is a result of their mutual connection to the tidal environment, as is shown here. So a probability distribution of the halo property that preserves its correlation with the tidal anisotropy should be sufficient to recover the correlation, any correlation it has with bias. This is what we would like to test. Here we can check this by shuffling the halo properties among halos in narrow bins of tidal anisotropy, and then such a shuffling preserves the correlation these halo properties have with tidal anisotropy, and then we take the sample and compare the 2-point correlation function previously obtained from the simulation with the shuffle sample. This is what has been shown here. The data markers are the shuffle sample, while the solid lines are the unshuffled sample. We can see that the shuffle sample considerably recovers the signal, and we also see similar behavior for other mass ranges that we have tested. Here is a closer look at what the form of probability distribution of C, which we choose to work with, looks like. Each of the different colors represent the 5 different properties, and at fixed mass and tidal anisotropy, the properties follow a Gaussian distribution, or they can be made to follow a Gaussian distribution after a simple transformation. The mean, variance, and the correlation with alpha are fitted as a polynomial as a function of mass and are shown here below. Together, we can write the distribution, conditional distribution of C conditioned on alpha and m to be a, of a form of a Gaussian form as shown here. We finally come to the algorithm which describes how to create the mock catalog. So for each halo in the large volume simulation, we can compute the mass, we can compute the tidal anisotropy, both of which are resolved, and use this to sample P of C given mass comma alpha. In low resolution simulations where halo properties are not resolved, we can populate the halos with internal properties by using this algorithm. So how well does the mock catalog recover the large scale properties, and how does it compare with a regular simulation? Here we compare how well the mock values reproduce the large scale assembly bias in the right panel and show a comparison with the simulation particle based computation in the left panel. In both panels, the halo bias as a function of halo mass is shown for 4 quartiles of halo concentration. The solid lines in the plots are reference curves based on a very accurate computation of assembly bias using the separate universe technique. At very large masses, where the halos are well resolved in both simulations and the mocks, both of them reproduce the assembly bias well. But at low masses, where the halo resolution becomes a problem, the mock performs much better than the simulation, as is apparent in the ratio plots below. This is not only true for halo concentration, but for all the other halo properties which we have considered. Thus, our mock making algorithm can be used to increase the dynamic range of large volume simulation, especially at the low mass end. Note that we do not use the information about the correlation between the halo property and halo bias for sampling the mocks, but retrieve this correlation naturally. So in summary, the tidal anisotropy around a halo is the primary driver of halo assembly bias, and as a proof of concept, we show that the 2-point correlation function of a halo of a sample shuffled sample of shuffled halo properties retains the same strength as the unshuffled version when the shuffling is being done in bins of tidal anisotropy. We also see that the tidal anisotropy is well resolved for halos whose particle count is between 30 and 700, the same region where internal properties are not resolved. We develop an algorithm that uses the tidal anisotropy and the mass to assign mock halo properties to these unresolved halos. Our algorithm will increase the simulation's reach in halo mass and number density by an order of magnitude, and it also improves the signal by percentages as large as 45% for the 30 particle halos. A future application and a promising application of this mock making technique is in the fast approximate simulations, where we can use this technique to incorporate assembly bias into the mock catalogs. Thank you for listening.